Right. So how it's going to gradually be
Yeah, we've
changing
got
because
yeah,
of the friction.
yeah.
Okay. All right. So like that would be a good. So
Yeah.
when Nelly is
Yeah.
saying that they're on stable orbit, so you
Yeah.
know like the orbit, and then
Yes.
you'll say that it's gradually changing the.
Yeah, no, the cool thing, so
Yeah.
we've got it in the script. So they're like, that question, so I'm trying not to, I won't vary the questions as much, but I want that way we know if we've got, like, if we're talking about the deorbiting maneuvers, then the video will come up. So that'll be happening while
Right.
we're talking,
Right.
and we'll see it
That's
there.
like I was yeah it was black yeah.
Okay.
One other thing too is
Yeah.
since this is a social media event, Nellie, you were really talking to Mike and looking at Mike the whole time. So there's a time where, like in the beginning, you can be looking at him, but then turn and look in this camera and tell
Okay.
when you're talking about some of these things.
Sure.
If you look into the camera, then you're connecting with the audience directly.
Yeah, and I think
Okay.
especially since questions are
And David
coming
did
from them.
that, and you did
Yeah.
you did some of that. And you looked at Mike, and you can turn back to Mike when you kind of like
When you're
finishing
wrapping up.
and so
Sure.
forth.
Yeah.
Yeah.
Right. But just
Okay.
this is where
Good
it,
point.
because it's social media,
Yeah.
they
Sure.
want to see
Where the
it.
people
Sure.
are.
Yeah, that's right.
Absolutely.
Like you're talking to them. And
Yeah.
Okay.
It's even better too when we start taking, especially when we start taking questions
Yeah.
from
Yeah.
that way. It's like, oh yeah, good question.
Right.
You know,
You.
we're not going to say who it is. I mean, we're not getting that
Right.
detail. You know, this is from
Yeah.
Astro Bob Stud from.
We're also used to speaking to the person that asked the question, and Mike
Yeah.
asking,
Yeah.
asking the question,
Yeah.
hey, tell me
Well, it's
about
a
this
different
orbit,
format.
so where's
Yeah.
the year?
Yeah.
That's
You
right.
know, you're always being
It's
polite,
natural.
and you're
Well,
looking
at
to
least
ask the
right. It's a
question.
different format. Sometimes too, when we're doing interviews, we're having you look at the questioner, and
Right.
that makes more sense.
Right.
It's weird when you're staring at the camera, but for this,
But in this case, it's,
It's
you know,
super
a little
appropriate.
Bit of that and then
Sure.
you know.
But I mean, you waving is helpful.
Yeah,
Yeah.
I mean,
When
so,
if
yeah,
Yeah.
yeah.
And that way, and then it doesn't mean that you have to be
Right.
It's just staring right at their lens. 'Cause I know that's odd, but you know,
Sure.
picture Mike's head right here.
Yeah.
Mike on a stick. So while we're waiting for that, we'll go
We
back
can
to
put
that
his
question we have.
picture above the camera.
So maybe the question, now maybe the question is we just talk about the how did we build them? So maybe it's a good description. Well, the spacecraft themselves are really not that big. They're the size of. I mean, I know that we used to have analogies for it. And I forget what they were, but describe like they're about the size of. I think one point we said a hot
It's-
tub, and then we didn't like that.
Yeah, no, it's actually it's bigger, right? So
Yeah,
it's the radius is 1 meter and it weighs like your Volkswagen.
It's 135 kilograms.
They don't know
No.
They won't know
kilograms.
kilograms for
No, I
yeah.
looked at the paper.
We have to tell
With
pounds.
the fuel?
No.
You have to tell it in pounds.
okay.
Well, pounds, yeah.
Well, it's twice.
Huh?
But even
it's
like, so how
roughly
big are
twice.
they?
That's
Yeah,
right.
yeah,
That's
but
what
you
you
can
should do.
multiply.
3 meters, so they're like
It's about 250.
10 feet across, right?
Or some object that people know. Like if it weighed as much as
Are
a
you
washing
ready?
machine.
So we will be able to share the graphics if you want to be able to talk to. We're going to send
We'll look
Okay, well,
program
need-
files
we'll
We'll
need-
look
let's-
and
I'll
let's
double
search
check.
it.
You'll be,
Yeah.
you know, this is kind of a little distracting, but you'll actually see yourselves. But then when you
That's
when you
okay.
look over here and you see video playing, you know that is actually going
What
out
they're
on the
seeing.
stream, and then you can talk about
I
it.
think that's better.
Yeah.
I
Yes.
mean,
And that way you know that if that, and then you can even say, well, as you see here, you know,
Yeah,
2032,
right.
et
I
cetera.
think it will
and
be-
then when it goes back to the wide shot or the close up, then you know that that graphic is ended and you're now there and that's when
Okay.
you know that's when it's still important to be looking here because that way if we
Yeah.
go from the graphic
about-
to you talking, you're
Good.
still looking right there
fine.
or you're looking at Mike or whatever. Okay?
That's good too. That would remind me to sit up.
Yeah.
Yeah,
that's-
and then we
all
all
of
need
us-
to do
all of us
watch our
needs to do
posture.
that. But we're good.
Wow, look at that! You're all sitting up straight.
I know. Well, now you're
See,
looking.
it's helpful.
As long as it's not going from top.
Okay.
So and if you're going to, are you going to ask about why couldn't we do all burns at once? Is
Yeah,
that-
yeah,
Are you
if I-
going to take it?
I can.
In this case, probably we should again show the
The perigee,
the
apogee.
this yeah.
Yeah, and say the further
you'll
side.
talk that
Yeah.
you know
The perigee,
right.
we can only do it in apogee, and apogee is only
No,
two.
right. The burn is it right? Is it apogee correct?
Yeah.
Yes.
So and the apogee, it's only 2 hours.
It's the farthest part.
Yes.
Right.
The
And we
longest
can
part
do
is
it
the-
in 2 hours. We
Right.
cannot
Yes.
complete the
Right.
burn. Yes.
Exactly.
I have a request for you,
Yeah.
Sasha. When you talk about if you remember, it's not essential.
Is that the
when
only
you
video
talk
that- was that
about
the first
think
video
one
we're
of
supposed to
those is,
slot in? I think it
science
was.
and the practical part, that's a fundamental aspect of living with a star, and NASA headquarters would
Ooh,
probably
that is a
enjoy
good-
just a reference. Someone should say it's part of the Living with a Star
Oh, yeah.
program.
Can I get a pen and? Does anyone have a pen?
Yeah.
Yeah, maybe
Because that I
erased
can borrow.
What you said will make the
I need
program
to
sponsor
take a couple
happy.
of notes.
it. Okay.
Just type the
Yeah,
acronym
yeah.
LWS.
Yeah, I know.
Just say LWS, and then they're happy.
Yeah, I knew they were smaller. I knew they were.
LWS, humans.
Humans, practical
Yeah,
science.
yeah. Well, if there's anything else, let
I
me
mean,
know.
and I think that's okay. Like, we don't have to
But-
say they're about. I mean, you get 10 feet. You know, I mean, they're.
But then I think that, talking about the booms is interesting because those are so.
Yeah.
Yeah.
It
That's
spans a football field, yeah.
Yeah.
It's 120 feet. It's 16 plus.
I don't understand feet.
I was
I'm
just saying,
sorry. I'm not
40
from around
meters?
here.
Well, that's half a football field. How's a basketball court?
333 feet with the booms.
So that's a football
no,
field then.
No, it's 120.
Meters? or
120
feet?
meters?
Yeah.
Yes.
So 300 feet. Well, more than
Gotta
300
do
feet.
feet. Gotta do feet.
Over a little bit and give everybody a little more room.
Sure.
Okay.
Span with DFW instrument bar booms fully deployed 101.
Thank you.
Get off, I'm gonna give you guys
Yeah.
just a little more room.
Yeah.
so you have room for-
So yeah, these are just little things to think of as we're talking about
60
describing.
meters.
So I don't
hold on.
slap David when
You
I
got
do
another
that.
Hey! The booms are that big! Whack!
And you're both down.
120 feet is.
So, see,
And they're
it's
spinning
two
wildly.
60 meters. Okay.
Yeah, this is good.
Okay, this is 50 meters. Or actually, it's 60 meters still. So it's 60 and 60 meters. It's 120 meters.
Those say too. It's too bad something that isn't the size of a basketball court to point out. Like the
And-
Oh,
tournament.
because
That's the tournament that everybody
Yes.
is probably else is watching right now. For those of you who aren't watching that.
So it's,
But I think we're at a good. No, we're not at a good because there's 330
Okay.
games,
So it's 102.
and then
Okay.
it jumps again to like 7. So.
Yeah, but I mean, I'm saying this is 60, not 50. But
I
it's
feel like
okay.
you have a little more room around you. So
Yeah.
you-
That's
Yes.
what Sasha tells me. But in the paper, it's 52.
Because
well, this
this
Okay.
is
is
the press kit that we
Okay.
put out at one.
Okay. Then let's
So I
do
don't know
this.
if we
No,
got-
no, no.
Yeah,
let's
it's
do
also
this.
a little bit
So
easier to
100
turn and not turn
120,
too far.
102, and then how much
Yeah.
Yeah.
meters? Well, how much?
If there's
meters
only
would
the
be?
room to do it, the
So
background looks good.
Spacecraft with like at full
Yeah, the background
Mhm.
looks
Like
good.
the
That-
belt just
Uh-huh.
coming right out of my head.
tip to tip
Yeah.
tree 33.
Yeah, like looks like
Uh-huh.
It looks like-
Saint
it looks-
Mike.
It looks like
35.
smarts. I've got.
What is that? Is it a football
Yeah.
field?
What I might.
Hey, Mike.
Yeah.
How big is basketball court?
I was just about
Should we
to.
move a little bit that way? No, or
I want to say it's almost. Let me say it's about 120 feet. Hold on.
I don't know.
It's 300, so we're going to say 335.
Splitting hairs here as they-
It's
Yeah.
about the size. It's a little bigger than a football field.
Yeah, okay.
Oh.
You had like an
So you had invite. Like, I've got this information.
See here, it says accommodated significant payload lasts 130 kilograms.
Payload mass.
that's the
What
payload.
happened
That's
to my
just the
space-
payload.
Payload.
The spacecraft is like 2 tons.
Oh, okay.
That's like that's a Volkswagen.
And that's a good analogy. People
Yeah.
can understand
It's a what?
that.
Volkswagen?
It's
the
like
It
that's
can't
what
be
I
a
drive.
BMW?
It's the mass of a.
I don't like
BMW.
BMWs. I'm a Volkswagen person. But we can look it up in,
Okay.
in the book.
Okay.
But it's just the instruments and the electronics.
I see.
It's nothing. I mean, these things are big.
Yes.
It's substantially bigger than the model that is.
I can be more excited. Okay.
They're doing a great job.
Okay.
It's
Okay,
94
I
feet.
waved my arms.
So football field is where.
This is incredible.
We should just have drinks for lunch.
Yes,
How
that's
about
right.
that?
300 football field's 300 feet, so it's
When camera one's on you,
for a football field.
zero.
We just spread them out a little bit.
Oh, you
No,
did?
300
Yeah,
feet.
yeah.
We just did.
100 yards.
We're kind of at a slight break here.
Then that'll be great.
Okay.
Yeah, we moved them. It was
Oh,
floating
that
out.
football field. So soccer field's like 100 and
All right, we're working on dimensions of sports
10?
fields now.
Right.
One of the main results from the mission was an accurate determination.
yeah,
of
100 yard
sport
plus. Yeah,
field
so
sizes.
120,
When you were talking
120
about
yards.
the non-linear
So
influence,
360 feet.
Huh?
like
So yeah,
if I
so
were you to
that's a
say
football
that,
field
like,
with
you
end zone.
found things that influence it, that
Goalpost to
are less
goalpost.
direct or
Of
that are
big.
unexpected or whatever you
Yeah.
mean by that.
You sounded like a scientist.
Sorry about that.
No, it's okay. That's why we're doing this.
What are the animation? Oh. So at the beginning, when David is talking about the belts, and we see the one animation, that should come up again when he talks about the 3+ belts.
Yep, could do.
And I'll tell them.
Okay.
So, when so the initial animation we show when David is speaking of the belts, Paulson, can you pull that up again when he's talking about the discoveries, because that's really where he talks about the three belt structure. So just roll it again. It's after Nelly talks. Yeah, I'm thinking that also. Well, let's discuss. I'm going to disconnect that. What do you want to tell me?
Okay. So we'll pick up. They're going to sort out the animation, but so let's try this because there's two clips that we want to use. So we'll start with a question about talking about the deorbiting burns. So they can cue up the animation. You can start talking about the details of the burns themselves, and then. Again, the last thing is, why are we doing 5, and why can't we do it in one long burn?
The second thing is,
And then
you lost the monitor here. Did you guys roll the?
we put in some segments from the new video, and then we start taking questions. So that's a good chance to practice the transition. I mean, I think there's decent flow here. This is good, right? We're going from,
Yes,
I mean, it's a
it's
good
natural.
story from the belts down
Yeah.
to science, the spacecraft, and I think that's working out.
Yeah.
We'll coordinate the graphics as we're talking through these last couple of questions, and then we'll just practice taking a few from what Jessica has already set up on the list.
Yep.
And then we can just talk about what we can do for the real thing later.
Right. Sounds good.
Okay. Thanks. Is this the?
He can shut you off.
Give me a sec to talk to them. All right, so we did that really fast.
Yeah.
And there was another video that they were rolling that we couldn't see. Do you think you're going to talk? Is there more you want to say? Were you comfortable with that level of info? What do you guys think?
I mean, do you want to explain more about the findings? Again, we'll add about the dangers of the belts to people,
Yes,
especially in light of the spacewalk today,
Right.
and then get into the hazards of spacecraft. It's also probably good. We talk about the lessons. We should probably address. I think and we could do it as a question later, or I could ask you about the importance of like what we learned from these. I mean, we built these to survive. A follow-up question could that be then, so what are the lessons in for future spacecraft? I mean, the value of that, we can get in a little bit more about how, what we've learned about this that will apply to, because Sasha brings that up about why it's important to study these.
Yep.
Maybe if there's something specific we can bring up about here. Is it?
What I would like to say is like mention that the amount of the shielding that is required, now we know how much it is to tolerate that radiation. But also we are going to explore a very new area that is 200 kilometers from, what is it, 200 kilometers in, how
No,
much is
in
it?
miles.
As a result of the
1.6.
changing mission.
No, like how much, do I need to say it in feet?
Yeah.
In miles.
Miles.
In miles.
In miles.
It's one divided by 1.6. It's about 120. I don't know, something.
About 120.
Yeah.
So we are
That's right.
coming
Wow,
from
I did it fast.
120 miles
I'm terrible at it.
from ground, and it's a new area, especially when we are talking about constellation of satellites. We want to deploy more satellites on low Earth orbit, understanding those and how to build the new generation of a spacecraft that can resist that environment will help us, like something
Yeah,
like that.
we can talk about that.
That's right.
Do we also want to throw it back to David to talk about the Helio fleet a little bit, about Van Allen?
Yeah, we should. I need to start.
Yeah. we can
System
do that.
observatory.
This is his heliophysics system observatory.
What are we going to talk? What are we going to say about this?
If you did ask me that, and if I pause for a minute, I'd say these are the spacecraft that are. There's a string of phenomena that connect the sun to the Earth. Heliophysics has sent out spacecraft to measure each aspect. The Van Allen probes are the ones measuring the effects that are of direct consequence to us right here at Earth, because they're measuring what's happening in the Earth's radiation belt, something like that.
Okay.
If I were prodded with that question. NASA's Heliophysics Division has sent out a fleet of spacecraft to track the sequence of phenomena that lead from the sun through interplanetary space to the Earth. The Van Allen probes are right here at the nub of that point, the place where the action is radiation in Earth's immediate environment.
Okay, so this is cool. So we should definitely make that part of our main conversation. Yeah, you know, I mean, that should almost be like where, like.
How does it fit in?
So I mean,
yeah,
you can fold it in right at the very beginning when you're talking about radiation belts. You know, you can say that everything starts from the sun.
Yeah. Yeah.
And to understand the system, we place the spacecraft, distribute the spacecraft everywhere from the interplanetary space to measure solar wind energy input.
Yep.
And Van Allen probes are situated at the very center of
at the center of
the
attention.
Hazardous.
Yes.
We can
region,
go
something like that.
Yeah, and we can also make that, because we start right away with the radiation belts, and then we get into the science of the radiation belts, we get into the spacecraft. We can also, before we start taking general Q&A, then take the picture back out and just say, okay, you know, Dave, we talked specifically about Van Allen probes and what we're doing right above Earth, but Van Allen probes are proud of a bigger network.
I find that easier. By the way, between now and later, we could find a picture of that network too that could be put up when we do that. That would be easy to find.
Oh yeah, it exists in one of my presentations.
And one question that we should remind me or ask me is, like, what happens to the end of the mission? Did I say, like, we cannot face our solar panels to the sun because we're out of fuel, and then?
So in the video that didn't play, that's the clip. It's you and Madeline discussing that.
Okay, good.
So I think it's a good setup to then come back and then really go into that.
Okay.
So is everybody okay? Can we start from the top and kind of go?
Yeah.
You don't have to, like, maybe
We'll do the
necessarily
whole
do all
thing.
the commentary.
Right. We'll just start.
See the flow of images. Make sure you guys.
From again? Oh, okay.
Yeah, from the top.
All right. Okay.
So we'll just set the introduction, then we'll start getting into the questions, and let me get back.
Everybody sit straight.
Yep.
The Van Allen probes have really provided us with more than 6 years of non-stop excitement, continually bringing us wonderful science results, incredible observations from the heart of the most intense radiation region that really humanity has ever found.
The radiation belts exist across the solar system and probably across the entire universe at all bodies that have their own magnetic field like we have at Earth.
But they are very, very susceptible to changes in the solar wind.
During geomagnetic storms, they can completely disappear and then come back with much, much higher intensity.
So spacecraft that aren't normally in them can suddenly become engulfed by them. And so it's really critical for us that we understand how these radiation belts are changing so we can better design spacecraft to be able to withstand unexpected dosage of radiation.
Well, good afternoon. I'm Mike Buckley, and we are live at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland. In fact, we are inside the Van Allen Probes Mission Operations Center here at APL. We have just begun the final thruster burn for Van Allen Probe Spacecraft A. Now, this burn, which is going to last about 127 minutes, is the final deorbit maneuver for the Van Allen Probe spacecraft, which had been in orbit around Earth since August 2012. There's a lot of important findings with this mission, and we're going to talk about those today. In fact, to talk about those, we have Van Allen Probe's project manager, Nellie Masavi from APL.
Yes, hi.
Van Allen Probe's project scientist, Sasha Okorsky from APL. And, oops, just lost my thing. And Van Allen Probe's Geospace program manager, David Sybeck from NASA Goddard. So we're going to first talk about the importance of the mission and studying this. I guess, Dave, let's just start with you. Why study the radiation belts?
Well, the radiation belts are our immediate environment. Circling the Earth are two belts of charged particles, protons and electrons, endlessly circling the Earth at distances of about 400 miles above the Earth's surface to a tenth of the distance to the Moon. The radiation belts were discovered almost 60 years ago by James Van Allen of the University of Iowa. He flew a rocket up, the United States' first rocket, Explorer 1, up into space. That rocket carried a Geiger counter, and that Geiger counter went off scale as it went up into space, and that led him to declare space is radioactive. So at that point, we knew there was a hazard out there, and we were very curious about it.
So at that point, right, it's then time to.
Yeah, I mean, you asked the wrong question. I would bail you, right? So you could just stop, and I would pick up, and I said if I can add something.
Okay.
So you know, you
can
can
pause.
pause.
His question.
Right, you did.
Oh, I said, tell us about the radiation belts. Yeah, sorry.
And that's okay because.
And now you can. Right. And now let me tell you. Now we really tell you about them.
So.
No.
Yeah.
Yeah, that's right. So tell us about the radiation. You described those. So then I would say, fine. Okay, so why do we need to study the radiation belts?
So we now understand that radiation belts in an extremely dynamic environment, radiation levels changes by orders of magnitude as the energy input from the sun drives it. The most remarkable thing, though, is that radiation belt particles are accelerated right here in the near-Earth environment and do not penetrate somewhere from the interplanetary space. So our near-Earth environment acts as gigantic particle accelerator. We also know that radiation belt-like structures exist at other space physics and astrophysical systems. In fact, every planet in the solar system that has magnetic field possesses radiation belts. So here near Earth, we have a natural laboratory to investigate and understand how particles, radiation belt particles, are produced across the universe. And of course, you know, like this is, you know, the science which we scientists are mostly excited about, but there are extremely important practical applications both for human exploration of space and for spacecraft design. In fact, there is a spacewalk that takes place now, and increased level of radiations is extremely dangerous for astronauts' health. So monitoring them and predicting them ahead of time, how they're going to change, is of fundamental importance of protecting human exploration. And second, of course, is that these particles also can damage spacecraft, and building predictive models is extremely important for protecting our space assets.
Right. So it says like the belts sound like a place where no human or spacecraft should really want to go.
No.
Right. But we built spacecraft to go into that environment. In fact, they've been there for 6 years. But let's go back to the beginning now and say, you know, how did we build the Van Allen probes? You know, and you know how to live and work in this hazardous zone.
Yeah, so we knew where we were going from the beginning, and our plan was to make a spacecraft that is bulletproof, that can resist not only you know, our mission timeline that was 2.5 years, but now we are operating 6.5 years with no hiccups. So what we built was a bulletproof spacecraft that was completely shielded. All the instruments, all the subsystems were thick shields, about 1/4 inch of shields. The materials that we selected, we made sure that everything is conductive. The blankets, from the blankets of the spacecraft, the grounding of the spacecraft, we made sure that everything has common ground, that we do not have any potential difference. So it was a lot of design thought process and collaboration between different disciplines, you know, making sure that everyone knows what needs to be done, a lot of design reviews. So it was a really big team effort to make sure that this spacecraft can, you know, tolerate those environments.
Describe them a little bit. I mean, you know, we just saw some animation of those, but how big are they?
So the spacecraft, it's about 1.8 meters. If I can have the model here, I would like to describe it a little bit more. So this is spacecraft. It's a spinner spacecraft. We have long booms. Like these booms are about 50 meters long. And so it's very incredible that these 50 meters, 40 meters, and 12 meters and 3 meters booms that we have, they are constantly making measurements. They are making electric field, magnetic field measurements. And the reason that we wanted them to be long, we wanted to be so far from the spacecraft, so we make sure that the measurements that they are making is actually from the environment. It has the solar panels, 4 solar panels that we need to constantly facing the sun in order to power the spacecraft. And you won't see the shielding inside, but it has a very thick shielding inside all the subsystems and the spacecraft, and it has a blanket that covers the spacecraft to make sure that the spacecraft is always in the room temperature.
Okay. There were 2 of them.
2 of them.
Why?
Yes. So it was very important that you are studying this kind of environment. You wanted to make sure that as the first spacecraft is making the measurements, the second one is following and give us more understanding if that phenomena that this first spacecraft measured, is it time dependent or is it a spatial dependent? So that was a very good way for our scientists that they can make measurement and compare the results.
Okay. So speaking of results, okay, so after 6.5 years in orbit, some of those results and the data that has come back from that have turned into some pretty incredible findings. So Dave and Sasha, I want to cover some of those important findings from the mission up till now.
Yes, Mike, these spacecraft and this mission have totally revolutionized our view of what the radiation belts are. Before their launch, we thought they were kind of a static place where not too much happened, that there was an inner belt and an outer belt, and they were just there. But one of the first discoveries from our mission was that the outer belt could almost completely disappear within a matter of hours, and it would be replenished with the appearance of a third belt. Then there would be 3 radiation belts, and sometimes 4 or even 5. This was a dramatic change in the way we understand the belts, and one that has prompted a lot more research.
I agree. In fact, as David mentioned, the radiation belts were the first discoveries of the space exploration era, and many scientists thought that this is a relatively well understood region that just simply need to be monitored in order to understand the space weather hazards and aspects. As soon as we started making measurements, we started seeing completely unexpected fundamental physics discoveries. Now, 6.5 years into the mission, we basically completely rewrote the textbook of radiation belt high energy particle research. So kind of to summarize it, so as you're looking at the screen, so it was previously thought that radiation belt intensities are shaped on the time scales of